Hello everyone, my name is Dan the Tutor. Today we're going to be covering standing waves, a popular concept in physics that has to do with waves, frequency, velocity, wavelength, a lot of that great stuff. Honestly, this is one of the most confusing topics in all of Physics 1, sometimes it's in Physics 2, so just keep in mind, yes, I know everything I'm about to say is confusing, but with just a little bit of practice, you too can master it. So first, let's start off with the concept of what a standing wave even is. We have three scenarios that we can potentially have. Let me just draw three shapes. The first one's kind of just a long rectangle. The second one is like a pipe with both ends open. And the third shape is like a rectangle with one side open. These are the three shapes that we can have. The top one is called both ends closed. The middle one is called both ends open, and then the last one is one end open, which you can also call one end closed, kind of like a glass half empty, half full. But the reason why we're looking at these three shapes is because these are the three ways that waves can propagate. So for the both ends closed, I want you to imagine a guitar or anything connected to a string, and how when you pluck it or move it, it goes up and down really fast like this. And you've probably seen this before where you look at a piece of string and it looks like it's in two places at once because it's going so fast. This is how we draw the standing wave, just like this. You'll also notice that at both endpoints it's touching the center. That's because these points right here, wherever it touches the center, are called nodes. And then in the center where it's like a maximum, we would call that the antinode, because it's the opposite of a node. And the classic example of seeing this in real life is the guitar. The guitar does this whenever you pluck a string. It vibrates up and down really, really fast. That produces a sound, and depending on the frequency of the sound, that's how we get different tones in music. Now with both ends open, it's kind of the opposite. The wave is going to be at an antinode at both ends because it will be at the maximum, and in the middle is where the node is located. So I would draw it like this. Now this one's harder to imagine in real life because the classic example that is used is like an organ pipe or pretty much any woodwind instrument. And as you can imagine, you can't really see airwaves, so you're just going to have to take my word for it that this is going on. This is the shape for both ends open. Once again, the node is in the center and the antinodes are at the ends. And then with the one end open, it's simple. You have one closed point here, the node, and then on the right side it's going to end on the open side, so it goes to an antinode like this. And the classic example of the one end open is a glass bottle. And you know this if you've ever had a glass bottle and you blow on the top of it and it makes a sound. This is exactly why. So in general, this is what's going on here. Now let's get into the specifics of what we're doing in terms of the math and the equations. So first we have probably the most important equation of all of today. It's velocity v equals the wavelength times the frequency. So if you imagine a sine wave, or a cosine wave for that matter, it looks something like this and it goes on forever. One wavelength is the amount of distance that you cover to get from one point to the same point in the wave. Now because the point doesn't exactly matter, you can pick any 2 points as long as they're identical. So for instance, you can pick the tops of the wave, you can pick the bottoms of the wave, that will also be one wavelength. You can even, if you wanted to, pick this point here where it's starting to slope up, and this point right here where it's identical in the path, that is also one wavelength. You can pick any 2 points you want. And then frequency comes from the fact that frequency is equal to 1 over the period. That t there, that is the period, and it's the amount of time that passes to complete one oscillation. So the units of period are seconds, and the units of frequency are going to be the 1 over seconds, which we never call it that. We call it the hertz, because that's the official name for it. Now let's relate this back to our standing waves. Specifically, we'll start with the both ends closed because that's the easiest example. So here is my wave. I could probably draw this better, but it doesn't matter. Notice here that only one of the waves matter. And what do I mean by that? Well, a sine wave can't exist at both places at once. It can only exist at one of the positions. Let's just choose the top one arbitrarily. And the reason I'm choosing that is because I need to know how many wavelengths is the blue. And to answer that question, what I would do is I would continue drawing this until I get to one full wavelength. And this right here is 1 lambda. We know that this is one oscillation. It's covered every point in the sine wave, which means that if I want just what's going on here, I think we can all agree that this is half of lambda, which is 1/2 wavelength. So that's important to know, because if I give you a length, let's say this thing is 4 meters long, the distance between these two nodes, then you know that the wavelength would be double that. Why is it double? Because we're saying 1/2 lambda equals 4. So 1/2 lambda equals 4. Multiply both sides by 2 to cancel out the 1/2. Lambda is 8 meters. So that lambda right there is 8 meters, which makes logical sense if you look at the picture. And why is that important? Because now if I know the speed of the wave, let's say I can make up a speed 300 meters per second for the speed of the wave, then that means V equals lambda times F. 300 equals 8 times F. And if you divide your calculator both sides by 8, we can get the frequency of 37.5 hertz. So that's the kind of question we can see with this problem. Now, another very important concept we need to talk about is that frequency we just found has a special name. It's got two names. The first name I'm going to give it is it's called the first harmonic, and you'll almost never hear it be called that. You're almost always going to hear it be called the fundamental frequency. So before I explain what the fundamental frequency is, let's talk about what the second harmonic is, the third harmonic. So let's draw a couple of these rectangles here. I'm going to draw 3 rectangles for us right now. All of them are the both ends closed case, as you can see. All I'm going to do is I'm going to change the number of nodes that are in each of these drawings. So for the first drawing, I'm just going to put 2 nodes like this and connect it like we did the first 2. The next example, I'm going to add another node in the middle so everything's equally spaced apart. In other words, now I have 2 loops going on here if you count the number of loops. And then for the last picture, I'm going to put 2 nodes in the middle, again evenly spaced apart, and it's going to look something like this. And the reason why I'm drawing all of this is because if you were to have this string, because this is what this is most likely, a string, that's what the both ends closed case is, and you were to swing it up and down fast enough at an inhuman speed, then you're actually going to get these shapes to start to emerge. And what we would call this, the top one is the first harmonic, or the fundamental frequency as it's called. The next one is the second harmonic, and the third one is the third harmonic. And it's easy to tell with standing waves which one's which, because at least for the both ends closed, all you need to do is count the number of loops. So in this one I have 1 loop, in this one I have 1, 2 loops, in this one I have 1, 2, 3 loops. That's how you can always count the harmonic for this case. And typically what we would write n equals 1, n equals 2, and n equals 3. What's n? Well, n is going to be the number harmonic you're doing. And the reason why we need to know that is because there's a way we can easily find the wavelength using a very specific formula. The wavelength formula for any of these standing waves, both ends closed, is simply going to be 2L over N, where L is the length of your pipe or string or guitar or whatever, or bottle, and N is the number harmonic. I don't know where the 2 comes from exactly, but we can derive it if you really want me to. But I would just take my word for it and use this equation to find the wavelength of any standing wave, and this will work for the both ends closed case and the both ends open case. It works for both, which is very nice. The one end open, one end closed uses a slightly different formula. We'll cover that later. And the other reason why the harmonic is important is because, let's just make up a quick example right here. If I say, for instance, the first harmonic is 200 hertz, then I instantly know the second harmonic and third harmonic, because each harmonic is just the fundamental frequency, which is 200, times the number n harmonic. So what does that mean? It means if I want to find the second harmonic, it's 2 times 200, so 400 hertz. If I want to find the third harmonic, it's 3 times 200, which is 600 hertz. If I want to find the 42nd harmonic, I can do that very easily. I just multiply 42 by 200, you'd get 8400 hertz. It's that easy. And this is true for every case. The both ends open, both ends closed, and the one end open, one end closed. It's true for all of them. Now for the both ends open case, again, this is our woodwind instruments, our organs that you'd see in like a church. If I were to draw the harmonics, at least the first three, so n equals 1, n equals 2, and n equals 3, I have to be careful how I draw it. Again, it is the number of full loops, except this time, whenever you have the both ends open, as you can see here, we have 1/2 loop, 1/2 loop. That's how it gets to a full 1 harmonic. So then with this one here, it's going to have 2 in the middle, and it will look like this. And again, the number of loops is 1/2. Here's 1 here. Here's another half. 1/2 plus 1 plus 1/2 is 2. And then if I wanted to draw the third harmonic, it would look something like this. This is much more difficult than the both ends closed in my opinion. But as you can see, the math adds up. The number of loops will always equal the harmonic number. And once again, we have the same formula for wavelength. Wavelength equals 2L over n, where n is the harmonic number. And we're going to use this equation, V equals lambda times F, for almost all of these. And then the last example we can have is the one end open, one end closed. And this one does follow a different formula for the wavelength. And that's because if you think about it, this is not half a wavelength. This is actually a quarter of a wavelength. Why a quarter? Because as we said before, in the both ends closed case, we said this right here was half a wavelength. This was half a wavelength. And this is half of a half, which makes it a quarter. So that's why that's a quarter of a wavelength. Now here's the thing. Let's draw, again, the second harmonic and the third harmonic for this one. So again, the first harmonic is easy. It's the shape we just drew. The second harmonic would be double the first harmonic, which would look like this. Now, there's a problem with this picture. The problem is it doesn't end on an antinode. So n equals 1, great. N equals 2 actually doesn't even work. I'm going to erase this because it's just wrong. So let's draw n equals 3 instead, which is 3 of these quarter wavelengths, if you think of it that way. And that's 1 quarter, there's the second quarter, and there's the third quarter. 1 quarter, second quarter, third quarter. There, now n equals 3 works. As you can imagine, we're going to skip n equals 4 and go straight to n equals 5. This is going to have 3 nodes like this, and it will look like this. And the reason why is because you count the number of quarter wavelengths. 1, 2, 3, 4, and 5. So notice for this one, you don't count the loops. You don't count the loops for the one end open, one end closed. Maybe you want to count the half loops. That could work. Here's 1/2 loop. Here's 1/2 loop, 1/2 loop, 1/2 loop. That's 3. 1/2 loop, 1/2 loop, 1/2 loop, 1/2 loop, 1/2 loop. That's a tongue twister. That's how you get to 5. Or if you don't like that, you can just memorize these shapes. That would work as well, I suppose. But again, it just takes some practice to get used to this. This is the first time you're seeing this, I assume. So, of course, you're going to be not very good at it. But as promised, the equation will be different for the wavelength. The wavelength will be equal to 4L over n this time. And instead of n being every integer, it's going to be every odd number. So 1, 3, 5, 7, etc. But again, we can use this harmonic fact to find the new frequency. So for instance, if this is 100 hertz, then the third harmonic will be 300 hertz, and the fifth harmonic will be 500 hertz. That still holds true. And again, this equation, V equals lambda times F, remains untouched as well. So now let's just finish today with a couple examples of standing waves, how they're used in action. Let's say that I have a both ends closed case. The length of this guitar, maybe it is let's say 2 meters long. And let's say the wave is moving with the velocity of 25 meters per second. What I'd like to know is, what is the fundamental frequency of the tone produced by the guitar? So again, I'm just using the equation V equals lambda times F, where V is going to be 25, Lambda just follows the equation lambda equals 2L over n. And if we're talking about the fundamental frequency, then n is 1 and L is 2, just like this. So it looks like lambda is going to equal 4 and then times F. That means F is going to equal 25 divided by 4, which is 6.25 hertz. And it's as simple as that. And once again, if I want to know the second harmonic, the third harmonic, whatever, then I just need to take that answer, 6.25, and multiply it by the harmonic number n, in this case 2. That would give me 12.5 hertz. And so that's how you can answer any question like that. Let's look at a different question. So this time I'm going to have the both ends open example, and I'm going to say the third harmonic is equal to 750 hertz. Let's say if this is an organ pipe, then the sound is going to be the speed of sound, which I know to be 343 meters per second. I'm not sure if you have to memorize that or not. And what I would like to know is, what is the length of this organ? Well, to answer this question, it's simple. There's actually two ways you can do it. I'm going to show you the way I would do it. The first thing I would say is V equals lambda times F, where V is 343. Lambda is what I'm going to solve for, and the third harmonic F is 750. So that means lambda is going to equal 343 divided by 750. That's going to be 0.457. And the units for that are meters, by the way. And once I have lambda, well, now I can say, okay, lambda is always equal to 2L over n for the both ends open case. And I know that n is the third harmonic for this one. So 0.457 equals 2 times L over 3. In order to solve for L, I need to multiply by the reciprocal. So multiply both sides by 3 over 2. That would cancel out the 2 and the 3 here and get me my final answer. And I'll get a length of 0.686 meters. And then another question I could ask is, if I have the third harmonic of 750, what's the fundamental frequency? For that, all you need to do is divide by 3, and that's because the first harmonic, we can call it F1, is equal to 1/3 of the third harmonic. So in other words, the fundamental frequency, F1, would be 250 hertz. And now let's look at one more example. This, of course, will be the one end open, one end closed case. Let's say the length of this bottle, or whatever it is 50 centimeters. And now I'm going to give you the following information. Once again, we'll use a velocity of 343 meters per second, the speed of sound. And I want to achieve a frequency of 1200 hertz. And my question is, which number harmonic am I using to achieve this? So in this case, I'm solving for n this time, which, if you don't even know where n shows up, we first need to find lambda in order to find n, the wavelength. So once again, V equals lambda times F. 343 is going to equal lambda times 1200. Divide both sides by 1200 in my calculator. And I will get lambda equals 0.286. Again, that's meters. Then if I want to solve for n, I just have to use the wavelength equation for the one end open, one end closed case, which is 4L over n. Now be careful here. You do not want to use 50 for L because that's in centimeters. We need to convert it to meters, which is by dividing by 100. 50 centimeters is 0.5 meters. So that means that lambda, which was 0.286, is equal to 4 times length 0.5 divided by n. 4 times 0.5 is just 2, so we can even simplify it down to 0.286 equals 2 over n. And then to solve for n, I need to multiply n on both sides. So then we get 0.286, n equals 2, and then just divide by 0.286. And whatever this is, this will be our answer. And it looks like, rounding to the closest integer, I'm going to get n equals 7. In other words, I want the 7th harmonic for this problem. And so that's how you conquer standing waves. If you have any more questions, please post them in the comments below. Thank you all for watching, and I'll see you in the next video. Bye-bye.